The ideal gas law. Sorry. Okay. As a reminder, an ideal gas is a gas that accomplishes all the statements, okay, of the kinetic molecular theory of gases that I gave you from the beginning, okay? So, what is the ideal gas law? Okay, it's a law that is based on the principles that your gas could act ideally. But the ideal gas law is the mathematical relationship between pressure, volume, temperature, and numbers of moles of a gas. Now, it is the equation of state for an ideal gas because the state of a gas can be defined by its pressure, volume, temperature, and number of moles. The equation that we are talking about is the one that you see over there. Now I'm gonna give you the key how I learned it. When I was your age, and I was told that I had to memorize the formula, the equation. This is the way I memorize it. PV igual NRT. That's how I memorize it, and it worked for me. I don't know if it's going to work with you, but that's my tip for you. Now, the letter P stands for pressure, V for volume, N for number of moles, R, which is a new one, is ideal gas constant, and we're going to talk about the constant a little later. And T, the temperature that is always mandatory to have it in Kelvin. Remember, if the temperature is in Celsius, convert to Kelvins. If it's Fahrenheit, convert to Celsius and then to Kelvin. Now, these are the possible isolations that you can use, okay? If you want to find the pressure, use the first isolation, the number of moles, the temperature, and the volume. Those isolations are good, so there is no excuse if you have it wrong. I hope you have everything correct. But it doesn't change that you have no excuse if something goes wrong, okay? Because I am also giving you the isolations. Now, this thing is very important because in the Google form that I'm talking to you about, I'm gonna ask you a few analytical questions about this slide that you see over here. Now, we have two situations, situation A and B. Now, what is going on in the situation A? Take a look. We have a container, and take a look at the size of the container. Okay. Okay. Now, I'm going to compare the size of the container. Do they look the same, or are they different? Just the container.
Are different.
Take a look at the length. Okay. And take a look to the width. What do you think? Is it different, or is it the same? And also take a look on how tall they are. What do you think? Do they measure the same? Do they look similar?
Yes.
Yes.
Yes. I mean, it's quite different if you analyze that one is a little bit, the degree of inclination of one is different than the other, but actually they have the same size. Now, take a look to the temperature, okay, and take a look to the pressure. What about the temperature? The temperature, is it the same or is it different? Take a look to the thermometers.
It's different.
Take a look to the thermometers.
It's the same.
It shows Okay, here is also 0, sorry. Okay, now take a look to the temperature. The temperature, it looks the same, but the pressure is different. Let's analyze, let's read a little bit to see what's going on. Okay, the collision rate of molecules per unit area of container wall depends on the number of molecules that are present. In other words, I mean, this is kind of confusing to read, but when I tell you what's going on, you probably understand better. So, take a look at what's going on here. I'm adding more gas into the container. Okay, take a look to how the particles are spread here and how the particles are here. Okay, in what container? 1 or 2? This is 1 and this is 2. In what container are the molecules closer?
In number 2.
In number 2, that's right. Now, take a look. Let's analyze, okay? Let's analyze a little bit. Okay, I'm hungry. Officially, I'm hungry. Sorry. So, let's analyze this. You go on a Sunday. Let's say that you go on a Sunday, you go to the beach. How's the traffic on a Sunday morning? Is it an easy traffic or is the same as Monday 7 a.m.? How is it? Is a lighter traffic or not?
No.
Sunday 10 a.m. How is the traffic? Light or dense? And how is the traffic on a Monday 7 a.m.? How is the traffic? Light or dense?
Dense.
On a Monday is
On
dense.
Ends
Exactly.
and on
Dense.
Sunday is light.
And the Sunday is light because many people decide to stay at home, okay? Many people decide to rest a little longer. So the traffic on a Sunday morning is lighter. In a Monday morning is hell. Let's be honest. No one likes Monday. And one of those reasons is traffic. So in a Sunday, because the traffic is lighter, it's less likely that people have a car accident. And the reason is because there are not so many cars. The cars are not so close, and the chance for you to have a car accident is be reduced by just knowing that there are less cars in the road. But on a Monday morning, even if that car accident is not going to kill you, you can hit your car because there are many cars around you. Okay, probably your fault, probably not your fault. Okay, that's not something of my interest. But all I want you to see is that the chance for having a car collision is being increased by just the density of the cars. How many cars are in the road, in the same road that you are traveling, is going to define the chance of an accident. Now, in gases, if you add more gas into a container, those particles now are closer one to another, and the chance for they to collide is being great. It's been a greater chance to collide. And when that happens, keeping the temperature the same and the volume also is the same because the container is the same and hold the same amount of volume, what is going to happen? Those particles are going to collide, and that is going to cause an increase in the pressure, as you can see right here. Okay, take a look to the pressure is closer to 0 in the first situation. The reason, you have less gas, less collisions. But in the second part, now you have more gas and the collisions increasing also will cause the pressure to be increased. This is the first situation that you need to know about gases. Now I'm going to stop this. Now what happens in the part B? In the part B, what can you notice about the size of the container? How is the size of the container? One is how compared to the second one? One is smaller, bigger, taller. How is it?
It's smaller.
Smaller. Smaller means that it can
Smaller.
hold less. Okay? It can hold less volume. Now take a look to the, again, take a look to the pressure. What happens to the pressure here? Is it the same pressure?
Yes.
What about the temperature? Is
Is
it the
the
same
same.
temperature? Also the same. Okay? Now, let's analyze this. It says, consider what would happen if the pressure and temperature are kept constant, while the number of molecules are increased. Again, here, I'm adding more gas. Okay? So, if I keep the temperature in the same, constant value, in the pressure also, I have the same pressure that I had before. According to Avogadro's law, the volume would increase. That's the change that happened in part B. By keeping the pressure the same and the temperature the same, if I increase the number of gases or number of gas molecules, is going to cause an increase in the volume. It's like, think about a balloon, okay? This is a balloon without air, and then you fill the balloon, okay? So what happens? You are adding more air inside the balloon, and then the volume increases. These are the two relationships that we can state about the gases and the ideal gas law. Okay. Now, to continue with the topic, we need to describe a little bit about the ideal gas constant. Okay. The ideal gas constant is called R. Well, in the formula, it's just the letter R in uppercase. It is known as the ideal gas constant. Now, that value, as I told you, is a constant, but that constant number is going to depend on the units that you have. For example, if you have ATM, moles, liters, and Kelvin, the value that you should use for R is this one that you see right here, 0.082055. And these bunch of units are the units of that constant. But this value is usually rounded to 0.0821 liters atmosphere over mole Kelvin. That position here of the unit is very important. Okay? Now, for example, in the case that you have volume in liters, pressure in atmospheres, and temperature in kelvins, this is the formula that you should be using. Now, there are many other values that we can use for R. For example, if I give you units of pressure in millimeters of mercury, the volume of R that you have to use is 62.4. But if I give you, for example, a pressure in pascals, you can use this number, okay, 8.314. But make sure that you have everything you need, because the volume, for example, should be in cubic meters in that case. So it is very important that you notice all these things. Now, I totally recommend the first two. For example, if I tell you that gas is at a pressure of 500 torr, which one are you gonna use? If I give you the pressure in torr, as you can see, any of them is given in torr, which means that you have to do a conversion. Now, there is a very simple conversion factor between torr and millimeters of mercury that says 1 torr equals 1 millimeter of mercury. So basically, they are the same. Okay? They are the same. So if I give you pressure in millimeters of mercury, you have to use the first value for R, that is 62.4. Now, how to use all these, you're gonna see how I do it in that video. Okay, so I'm gonna share with you a video